Hello, everyone. Welcome to this webinar. Good morning, good afternoon from wherever you may join us. I'll give a few seconds for some more people to gather and we'll get started. So in the meantime, I'll start with a little introduction about myself. So my name is Carles Bosch Padrós. I'll be your speaker today for this webinar. And in this slide, you can see a little bit about myself and my career, what I have been up to so far. And I have 8 years of experience working with EDEM and also in the DEM industry. And at the moment, I'm occupy the position of EDEM deputy within Altair, and I work also in the pre-sales team. So helping our existing and new customers be able to deploy EDEM for their applications. And that happens inside the global technical team. So I can help people all around the globe. I'm sitting in the Barcelona office of Altair with some other EDEM colleagues there. But as I said, supporting the whole world from there. And moreover, for the specific topic of today, I have been directly involved in I would say, the beginning of this project, which is the breakage model and modeling comminution and breakage in EDEM. I have been involved from the very beginning of this project, and I think I'm really happy and really proud today to be able to share and go over this webinar with you. Today, I want to talk about discrete element breakage and fracture modeling in EDEM. And these are the contents that I'm going to touch on today's presentation that should last around half an hour, and then we'll have some time for questions at the end. And then we're going to talk about a case study at the very end, practical example, where breakage was used by one of our customers. And finally, we're going to see also some theory. We're going to talk about the way to set up the model in EDEM and some practical cases where it can be used. I think I want to highlight the idea of today is not necessarily to go very deep on all the mathematical content of the model, but I think it's important to give an idea of what's involved in terms of equations and so on, which we also will see. So let's move on and let's start with the introduction and about the topic we are going to talk about today, which is particle breakage. And this phenomena of size reduction, comminution, or breakage, has many names, is present on many different industries. And I think you can think of probably mining at first, steel making, things like that, mineral processing. But also, sometimes we need to think that this breakage sometimes is the goal of our process and what we want to achieve.
Carlos, sorry to interrupt. Albert here, just on the back end. The poll looks to still be open for me. Could you stop sharing your screen and then reshare it again? It looks like we can't see your slides.
Sure, the polls are closed, but let me do that. Sure, I'll reshare my screen in a second.
Yeah.
Okay, so resharing screen right now.
There we go. Yeah, we're all good now. Yeah, it looks like the poll thing had bugged out a little bit. Awesome. Okay, sorry.
Perfect.
I'll go away again. Bye.
Okay. So yeah, I'll start over after this small technical issue. Apologies for that. But yeah, introduction to particle breakage, which is a very common phenomena in the different industries. So initially, you can think of mining probably or steel making, but actually powder-related industries also observe and also are interested in breakage phenomena. And I think something important to understand today is that sometimes this breakage is actually the goal of our process, and through through the application, we are trying to reduce the size of the material, or sometimes actually breakage is a result that it's not wanted, it's a non-desired result. And either way, it's good to have the tools to be able to model that and understand when that phenomena is happening. As such, as I was saying, being able to predict that breakage and to understand when breakage, whether it's desired or undesired, will happen in your process can be very beneficial for several reasons you can see in the screen. So first of all, we can improve the efficiency of our process, make it faster, and make it more accurate in terms of the way we obtain the final size reduction that we are looking for. But also we can do it to increase the equipment life. So thinking about mining, things like mills, cone crushers, they experience very large wear. And these equipment are very costly to repair and bring back to life. So any improvement that can be done on that front is a great benefit. And just simple power consumption as well. So if we have a more efficient process that can reach the breakage state that we want with a less or smaller power consumption, that also brings great benefit to the company or to the process. So I guess before talking about particle breakage itself and the process and the modeling, I want to touch briefly on just general application of DEM for these industries, because I mentioned breakage is relevant in mining, it's relevant in steel making, in several different sectors. And in these areas, EDEM has been used already for many years to simulate breakage-related processes. Most typical ones being, for example, mills, that you can see this video from our customers, Tega, and also things like crushers, jaw crushers, cone crushers. All these equipments are very typical to be simulated with EDEM. And EDEM is able to produce a lot of data for this type of equipment, things like flow behavior of the material, how it is inside, the throughput, consumed power, things like that. But in terms of breakage specifically, EDEM is producing a lot of data about the particles interaction and particle impacts, contacts that can be used to predict breakage if we have the right model for it, which is what we're going to talk about today. Our breakage model, so-called EDEM Tavares UFRJ Breakage Model, is going to be the main topic for today's discussion, and has been developed by the University of Rio de Janeiro and Professor Tavares for a long research over more than 25 years, a lot of experiments and a lot of validation. And within the EDEM team, we picked up that work in collaboration not only with Professor Tavares and the team at UFRJ, but also with Professor Oy in the University of Edinburgh and the internal team at EDEM, of course. Things that can be found in that model, or things that are considered in the breakage model, is the probability of breakage of your material, the size of the material, how it affects the breakage probability. Smaller particles will have a different breakage probability than bigger particles. But also, something that I consider to be very important is that a particle can be weakened if it doesn't break. So we're not talking about yes or no breakage and that's all. We're talking about we break, we don't break, but then if we don't break, we've probably already damaged the particle, and we need to take that into account. And some key features of this model is that we are using a very efficient particle replacement approach, which I will touch on in a slide later on. We're using spherical particles, which is basically the methodology that the model has been validated for, and I'll touch on this more later when I talk about the fragment replacements and energy calculations. And also in EDEM, we have very advanced post-processing tools specifically dedicated for that model that will allow you to see great detail of the data produced when a simulation is run with the EDEM breakage model. A quick example, just to get you a bit of a flavor of what we're talking about more in practical terms, is that cone crusher, which is coming courtesy of Professor Tavares. And on the left side, you can see the cone crusher equipment processing a few particles. In that case, they are colored by mass, and the clearer color, the clearer particles obviously being smaller. And on the right side, we can see a typical and very intuitive analysis that one would do on an equipment like this. So trying to understand the final size distribution, or the processed size distribution of the material after it is broken by the crusher. The blue line refers to the feed, so the material that comes in, and the red lines, actually the red lines are the results of the simulation in terms of particle size distribution, and the red squares are actually the experimentally measured results of that same process. So you can see there's a very good and very reasonable agreement between what the simulation can predict and what the experiments have collected. So let's dip a little bit into the model theory. As I said before, I don't want to go too much in detail or into a lot of the mathematical side of things. I want us to be a little bit more practical, but I think it's important to understand where things come from and that we are not doing any magic here. We are talking physics and we are talking science. So the first thing that we need to know is that the model was originally developed for rocks and ores, traditional materials and minerals that we find in the mining industry. But it has also been validated for steelmaking materials, other minerals like coke, sinter, or different types of pellets, for example. But however, the breakage model has actually been tried in other frameworks, such as like powders and this type of materials. And it's also promising as a framework because sometimes it requires some changes or maybe to adapt certain parameters, but it has a lot of potential to be used outside, let's say, the initial materials where it was conceived for. So a lot of potential to be applied in many areas, as you can see. In general, the applications, as I said at the beginning, are two. One is to understand the desired breakage and to be able to know what is the size that your material is going to have after we break it. The other type of application is to understand whether we are damaging our material or not. It's not a breakage that we want, but it's a breakage that we want to know if it happens in our process. So either way, this model is suitable. This essentially means that potential users are equipment and supply manufacturers, of course, making mining equipment, obviously size reduction equipment. Steelmaking companies, they make use of this model as well. And obviously research centers and any other company that wants to investigate the breakage process, as I said before, is a great framework for any breakage process, regardless of the material. But you know, might need some adaptations depending on how your material behaves. Moving on to the applicability of the model, I want to start by saying that a key feature of this breakage model from Professor Tavares and UFRJ is that it is able to capture the breakage happening from low stressing events, or so-called surface damage, and also able to capture maybe the more traditional or the more straightforward breakage that we think of, which is a catastrophic event where a particle or a rock just splits into many parts and we cannot see any resemblance of the original particle. A surface damage or a low stressing event would be, as you see in the picture here, would be the case of eroding a little bit the surface and just losing a little bit of mass, but overall keeping the initial particle pretty much as it was. So the calculation cycle, or in other words, what happens when we run a simulation with the Tavares model inside EDEM? Well, the first thing that we need to do is to populate the model with the parameters that belong to the material of interest. We're going to talk about this shortly. But then after you have defined your parameters and you start running your model, EDEM takes care of calculating the contacts and the impacts that happen between particles and the surrounding equipment. From these impacts, we derive an impact energy that's arising from this phenomena of this collision. And this impact energy is then measured against the resistance energy that every particle has. And if that impact energy is bigger than the particle resistant energy, that is called fracture energy, we're going to talk about in the next slide, then in that case, we actually break the particle. But if the impact energy is not enough to break the particle, which means the impact energy is smaller than the fracture energy of the particle, then we go into damaging the particle, that low stress surface damage scenario that I have talked in the previous slide. Looking at the bottom left of the screen, if we have enough energy to break the material, what we do is we go through the T10 replacement algorithm, and we find the right fragments for this breakage event, and we replace the original particle by the selected fragments, and we carry on with the simulation. The loop starts all over again, and we always keep calculating whether we have breakage or not. So for the fracture energy, it's very important because it's essentially the parameter that will dictate how much energy a particle can hold before breaking. And this energy is assigned depending on the parameters, the input parameters that you give to the model, as I said before, and it's based on a log-normal distribution. You can see the equations there. And I just want to highlight that you can see here in this site that the diameter of your particle actually plays a role in that energy, fracture energy allocation. Smaller particles will tend to have a bigger fracture energy. You know, it's harder to break a smaller particle. That's for example. But if you look at the right side of the screen, you can see a typical plot, the reference at the bottom as well, of a distribution of fracture energies for different materials. And also inside the software, inside EDEM, we have a slice of a mill, and we can see that the particles are colored by fracture energy. So there is a distribution of fracture energy, even though all the particles belong to the same material and to the same breakage properties, but the distribution is applied and we get non-homogeneous fracture energy in the particles, which is what you would expect from reality as well. So even though you have two rocks from the same material, not each one of them will break under the exact same type of impact. So we're replicating reality here. So when breakage event happens, as I mentioned in the previous slide, we go through the T10 calculation. This T10 calculation is essentially the equation that you see on the left side of the screen, which tries to work out which type of combinations of fragment sizes and fragment numbers will be introduced when the particle is broken. And that, amongst other things, is depending on the ratio of impact energy and the energy that your particle can hold before breaking. So if we have a type of impact that surpasses immensely the resistant energy, we'll have more fragments being created, and the T10 will actually reflect that. So what you can see on the right side, this image here, which is in that case is a text file, this is actually inside EDEM, and you can see that T10 equals 1, 1.5, 2, 2.5, and there is an immense list of T10s, and each T10 has several combinations of fragment numbers and sizes. This first column is a percentage of the particle volume, And each number here is the number of fragments that will have this volume after they are created. This essentially allows us to show a realistic variability of the results. So if you take two rocks of the same size, of the same material, and you break them 2 times with the same energy, they will not split in exactly the same number of fragments and exactly of the same size. So with these different combinations, you need to think about the families vertically here. We make sure that we capture reality and we have a variability of fragment distribution, even though the material is the same and it might break under the same energy. Looking a bit deeper into the fragment generation, after we have this theta value calculated and we select a family of fragments that, remember, the family dictates how many fragments we put and of which size they are, we then remove the original particle that I like to call is the mother of the fragment, so the mother particle. We remove it and immediately we place those fragments from the chosen family and we put them super overlapped. You'll see some images to follow, occupying the 3D space of the original particle. So we try to disturb pretty much zero the simulation that's ongoing with this replacement. This methodology also ensures that the mass is maintained because the number of fragments and the size of the fragments that we pick is such that the overall mass of the original particle is still maintained if we put all the fragments together. And we are also able to place all the fragments that the family requires. So since we are putting them overlapped inside the particle, I'll play the video again, you will see how all the fragments are immensely overlapped. And this allows us to make sure we include all the fragments for an accurate particle size distribution, which subsequently will mean that we will have an accurate result for successive breakage events as well. So we will overall have a very high precision on the size distribution of our material. That's one of the main reasons why using single spheres is beneficial, not only for the also for the replacement of the fragments and making sure that we place all the fragments that we need to place. Let's move on and let's talk just a bit more about the fragment replacement and the damping that we can apply. If you look at the images on the left side, what we have is an image of what happens when a particle is broken and we place the fragments inside. And then it is also very important to know that the fragments are placed perpendicular to the largest impact of direction. So you can see these black arrows, they show the direction which the particle has been impacted, and the 2 biggest fragments are placed perpendicular to that. This is to account for, to be as close as possible to experimental results. Apologies, everyone. I just close the window for the outside noise. Apologies. So I was talking about the global damping rule and the way to make sure that the particles, even though they are highly overlapped, as I said before, they do not explode, because you can imagine that in DEM, when 2 particles are highly overlapped, this brings high forces and hence an explosion. So there are a couple of parameters in this model that allow you to control if you want to damp and slow down the release of the fragments. So another important topic and also a key feature of this model and its application in EDEM is the fine particle generator and the appearance of what we call dummy particles. So I said before that this model represents subsequent breakage events. So you break one particle, and it continuously breaks. There is no, there is no specific limit necessarily on a theoretical level, but you can imagine that the more we break, the smaller our particles are, and the smaller they are, the longer it takes to calculate the simulation. Time step gets involved, number of particles as well, and it all contributes to a longer model. In that case, what we do is we essentially have a way to define a particle limit size of which the particle cannot break anymore, but we will flag it as a dummy. And by doing that, we allow at the post-processing stage to calculate the particle size distribution that would come if this dummy particle would have broken. So in other words, we get to post-process a full size distribution without any particular size limit, but without the need of simulating absolutely every size, which is very beneficial for the computational time. And before we start talking about practical things, it is very important to touch on calibration as well, because to get accurate results that we can trust, we need to make sure we calibrate and adjust the material. And this is usually done with an experiment that should be done for either a single particle or a small volume of material, because we want to keep things simple and easy to measure, and we want to have ways of collecting experimental data as simple as possible. And it is very important to be able to control the energy that we put into the impact. So if you look at these images in the screen, there are different tests that essentially in different ways try to break the material. But in all of them, you can control how much energy goes towards the impact. So then we can know and we can refer how much energy contribute to a specific fragmentation. It's very important, of course, that when you do the test, you are able to not only control the energy, but also collect the fragments and be able to count how many there are and of which size. And these three examples, just for reference, it's an ultra-fast load cell on the left, a uniaxial compression test in the middle, or a pendulum impact on the right side. So I want to briefly talk a little bit about the setup or the workflow of the model. And these are all the inputs that are required if you're gonna run it. There's a few of them I will explain. So the damage constant is basically controlling how much we weaken a particle after an impact that wasn't enough to break the material. And then global damping, strength, and time. I've already mentioned what it does, try to make sure that the fragments do not explode. They're not always necessary. So it's just kind of in case you have a very compacted system, you may want to make sure your fragment release is controlled. And then the rest of the parameters, especially infinity, E50, and the phi fitting parameter, they will characterize and they will affect the fracture energy of your material. So they will dictate how much energy your material can withstand before breaking. With the sigma, we apply standard deviation to that fracture energy. I said before that it's a distribution, so that plays a role. And then A and B will affect the calculation of the T10. And remember that T10 specifies the number of fragments and the size of these fragments that we choose after breakage event. And then very important also to look at the D minimum. As I said before, the breakage model can break the material infinitely. So we want to put a limit on that. Post-process those sizes. We will not take care of them in the simulation time because it will slow things down. We also have a minimum collision energy, which means that if an impact is very, very small, we will actually not count it towards breakage. So when you work with EDEM, I will touch on this very, very quickly because I think it's It's few clicks, so very straightforward. You will create your material. In that case, it's a granite, and you will make a copy of it, or at least that's how I would recommend to operate. You make a copy of it, and you rename the particle of your granite material. You rename it with _dummy. Remember, that's the dummy particle that refers to those particles that will not be broken to save computational time, but they will be post-processed to obtain a full particle size distribution. Once you've done that and you've copied your material, you've made sure that you named your particle as dummy, you move to the physics section and you select the Tavares UFRJ Breakage Model, and you click on the configure button. Here's where you have all your parameters to be defined. This needs to be calibrated, as I said before, but to help you start with, there is a library of breakage parameters of, I would say, most common materials that is available with your EDEM installation. So refer to that for a starting point and also for a maybe fine tune for a later calibration. Very quickly on the simulator, when we are going to actually run the model during a certain time, it's important that the time step that we define, that's typically 20%, 2040 for regular DM flow simulations, we bring it down actually to around 5% maximum, but we need to make sure we select the 5% of the smallest fragment that we will have. So the V minimum, if you remember for the previous slide, we defined a V minimum here. This will be the smallest particle in our model. So the time step should be around 5% of that smallest particle. And I recommend to run the model on GPU, which EDEM has a great GPU implementation of the model for fastest runtime, which obviously is preferred. Just one thing on the post-processing. I've been talking about these dummy particles and how EDEM can, without simulating them, it can actually calculate the size distribution. So once your model is done, you just go to the analyst, click on the file export. There's an option there, breakage particle size distribution, brings up this menu here, where you select a few details like the time step that you want to process or the range of time steps that you want to process. And then what's your particle, your dummy particle, the minimum particle that you want to plot in the graph. And then when you do the export, you get these graphs that you see on the right side. So it's a typical particle distribution, particle size distribution graph, where you can see that we complete, let's say, all the distribution. So we don't have a limit. We start having data really close to zero. And that basically is thanks to the dummy particles and the post-processing tool that is able to calculate the fines at the post-processing stage without having simulated them before. So we save that time, but we still get all the good data. And now I will finish up with a quick example from Columbia Steel, customer we collaborated with some time ago for this great case, which is about one of their cone crusher designs. A little bit of background on this case. So cone crushers, in case you do not know, are a very common size reduction equipment, especially in the mining industry, but in other sectors as well. They come in different sizes, and they induce what we call catastrophic breakage to the material. So they're very harsh on the particles that go through them. This means that there is a high operational cost in terms of power consumption, but also in terms of life of the equipment. So as I said before, any small improvements that can be done to this equipment brings big savings on the operational costs. And to that point, Columbia Steel had come to us and presented the question of verifying that their new design, which is what you can see currently on the screen in these three views, their new design was approximately 10% faster and offered a 10% throughput than its predecessor. So we utilized EDEM to demonstrate that, and actually there's a lot of other analysis that has been done as well that show the powerful work environment, or virtual work environment that EDEM can provide for cases like this. So let's have a look at some of the results. So on the left side, you have the new design that was supposed to have this increased performance, increased throughput. And on the right side, we have the predecessor, the original design. So I'm going to let the two videos run, and we really want to see the new design processing the material faster, which I think it's already obvious that the new design is working at a faster pace. And if we let the two animations finish, we will see that actually all the material is processed in 37 seconds for the new design, while it takes 44 seconds for the predecessor, for the previous design. If we plot the results in a graph, this is what we obtain. So obviously slightly higher in blue for the new design, and the throughput finishing earlier because the process and the cone crusher is emptied sooner since the throughput is higher. So nothing surprising there. Some other analysis for reference. So the particle size, of course, we are crushing it down, so you can see the diameter is changing a lot of the material. And moving on from that, also compressive forces were of interest for Columbia Steel. And you can see that they are plotted here into average compressive force graph for the new design and for the predecessor design. Not a lot of differences in terms of the force that is induced in the material. And the last topic I wanted to touch on today, which is about further possibilities and how to build a more advanced system with your either cone crusher or whatever equipment it is that you are simulating breakage with. And it's with the addition of multi-body dynamics, which in the case of the Altair ecosystem, we're talking about Altair MotionSolve, which can be easily coupled with EDEM, which means that the MotionSolve, the multi-body dynamics tool, will control what's happening with the equipment, and EDEM will only control what's happening with the particles. And they will have, these two solvers will have a dialogue and will pass information to each other, but each one of them will take care only of their separate matters. This means that we can impose real power to the mantle if we're thinking about the cone crusher or to the equipment. And we can also post-process what has happened to the equipment. So we can understand how the forces have affected the equipment, the rotation, the movement. And also we can understand the power required or the power that we have needed to simulate that system, to know it in advance. And just because if we simulate in EDEM and we move with kinematics, we are essentially enforcing a displacement, which in other technical terms could be like applying an infinite force, which gives a good simulation result. But if you are interested in understanding what happens to the equipment itself, you may want to bring in multi-body dynamics and Altair MotionSolve to get accurate data on that. Okay, so that brings me to the end. So with the summary slide of the topic we've presented today, which is the EDEM Tavares UFRJ Breakage Model. So to recap, it is based on experimental data collected over more than 25 years of research by the group of Professor Tavares. And in general, it is applicable to rocks, ores, and other minerals, even though, as I said before, it can also be used in other areas, in other types of materials, but might need more work in terms of setup. And the model can capture both high and low stress breakage events, surface damage, catastrophic breakage. And it is fast and accurate thanks to the single spheres methodology used and the GPU implementation in EDEM. And a key thing of that is that you can post-process very fine particles without actually the need of simulating all of them. So we save simulation time, but we don't save accuracy of results. Also, running the model in EDEM allows you to benefit of the rest of the Altair tools that can couple to EDEM. I have touched on MotionSolve, which is probably the most direct one for a case like this, but you can also couple EDEM to CFD solvers and to export results to FEA solvers as well. So take that into account, that you can benefit of another set of physics that are there in the Altair ecosystem. And last but not least, the model is in constant development and improvement, of course, together with the group of Professor Tavares. So yeah, you should look out and stay updated with the changes and the improvement we make, because it's really an exciting topic. And I think that's all from me today. So thank you very much for your attention and for your time. I think as I close the webinar, you'll be given a survey. So I would greatly appreciate if you can answer it. It will help me a lot. And yeah, other than that, I'll just wish you all a very good day. Yes, Albert?
Yeah, there's a few questions for you in the questions panel.
Ah, I didn't see them. Sorry about that.
No worries. There's a few questions that have come together there. Do you see them, or I can read them out to you if you like?
I see them. Let me just make the window bigger. Okay. Can I just pop this out?
Yeah, you can. If you just click the thing and it'll bring out.
Okay. So, yeah, so first question says about a library for the breakage model, such as the GEM database. So someone that's already familiar with EDEM and its tools. And I think the answer in general is yes. So we have a library. I would say there are like around 20 different materials and the breakage parameters that you need for each one of them. But it's not as comprehensive as the GEM database. So it's not as detailed as the GEM database. The GEM database is already a test performed with these parameters with a given result, and it has a wider reach. It has, I think, around 60 or 70,000 different material models that you can choose from. The breakage material library that we have is more reduced, as I said, around 20, and you can definitely use the parameters there. They are good parameters that have been taken from Professor Tavares' group. But I would say typically better to use them as a starting point for adjusting them further yourself later on.
So, Carl, they can't see the questions, so you'll have to read out the question as well as the answer.
Okay, sure. So there's another question as well about parameterization. So parameterization is one of the most important works to be done in breakage simulation. Most of the industry does not have proper instrumentation to do so. How do we recommend the study to be taken place? Does it make any sense to send the information to Altair team or to enter in contact with Professor Tavares to better result? Very good point. A very good question. I would say we've done both things. So obviously, Professor Tavares' group is a world-leading team in that matter, no doubt. So getting them involved is always beneficial. But I would say that one can obtain the required information for the breakage calibration if you have access to the equipment that, for example, the ones that I have shown in the slides. So if you have access to that equipment, you can obtain all the experimental data and calibrate your material, or you can send it over to Altair and we can work together to calibrate your material. If your material presents some sort of complexity or perhaps escapes a little bit the typical intended applications of that model, we would always get Professor Tavares involved and get his input and his comments to how feasible and how doable it is to characterize that material. More questions. So common problems during application of breakage in EDEM. I wouldn't say there are common problems. I mean, I would say maybe there are no problems. I would say something to look out, and I would like to highlight that I mentioned before is simulation time. So we want our models to run fast, and the breakage model has a lot of tools and features to make sure you run fast. I talked about GPU implementation. I talked about the dummy particle and how we can model small finds without the need of simulating them. So all these things are key to speed up your model, but you always need to look out and make sure that you select the right minimum particle size that you want to see in your model and that you define the time step correctly. So these things, as I said, they are not problems, but they are key things to look out to make sure your simulation is correct and accurate. So more questions. I think we are coming towards the end of the questions and also the end of the time. So thanks everyone for sending the questions. So this one says, I see the future of the application for the EDEM breakage model to reduce energy requirements on the comminution process. Does it make sense? Does it already give support to the industry application in this field? Yeah, so I guess the answer is yes. So one of the key areas that the breakage model can help with is the understanding the power consumption and try to make a more efficient process that can reduce that. And we are already supporting our customers with the breakage model and its application. So the model is already available in the platform and our customers are using it out there. We are supporting them regularly with it. So I hope that answers all your questions. So if there are any other questions, I'll be able to take them offline via email or whatever other methodology that you get the questions up to us, if you have requested a follow-up as well. So I think that yeah, probably we can wrap it up here for that webinar. So thanks everyone for joining, for the questions, and for your time. And yeah, I hope to see you again soon in another webinar, or we'll get in touch in some other way. So thank you very much and have a great day.